So we have the theory of linear approximation. Namely, if the function's terrible, then we'll use the equation of a tangent line for a value that's close to x, right, like say a, and we'll use that equation of that tangent line to approximate what the f of x value is. That's all kind of theoretical, so let's actually do a problem. So we're going to consider the function f of x equals the square root of x. Right, a classic example of something that the calculator doesn't really like to do, right? It doesn't really like to deal with the square root of 1.1. It much rather, and all of us would much rather deal with the square root of 1, the square root of 4, the square root of 9, and so on. All right, so we're going to find the linear approximation to the function at the value x equals 1. So remember, this is the linear approximation. So I need f of a, I need f prime of a, right? And then x minus a is fine because I know my a value is 1. So you can see right here, x equals 1 is telling us that a equals 1. Right? They're giving us a particular value, right? So that's constant. All right, so we know a equals 1. If I'm going to find the linear approximation, I'm going to need to know what f of a is and what f prime of a is. So let's start with finding f of a. F of a would be f of 1, which would be the square root of 1, which is 1. Great. Then I need f prime of x in order to be able to find f prime of a. So f prime of x would be, well, remember, this is x to the 1/2 power for my function. So f prime of x would be 1/2 x to the negative 1/2, also known as 1 over 2 square root of x, like that. So that means that f of a, or excuse me, f prime of a would be f prime of 1, which would be 1 over 2 times the square root of 1, which is 1 over 2. All right, I've got my f of a, I've got my f prime of x, which may make me find my f prime of a. Wonderful. So that means that the linear approximation itself is f of a, which is 1, plus f prime of a, which is 1/2, times x minus a, and a was 1 for us. Wonderful. All right, so part A is done. We have our linear approximation. Fabulous. You don't have to distribute or do anything like that. We're fine right there. Letter B, we're going to use that linear approximation to estimate the value of 1.1. Okay, so if I want to approximate square root of 1.1, my x value, so approximate, I'm sorry, that's off screen, square root of 1.1. Okay. So part A, sorry, was to find L of x. That was what part A was. So that would mean that x for me is 1.1. Okay. So then I'm going to use the function value that I found up above. I'm going to say L of 1.1 is equal to 1 plus 1/2 times 1.1 take away 1. And I'm using the L of x I came up with. All right, so that's 1 plus 1/2 times 0.1, so that'd be 0.05. So this would be equal to 1.05. I'm just doing that math in my head, but I can prove it to you. Let's think. I could do Desmos for starters. I could say, all right, find me 1 plus 1/2 times 1.1 take away 1. There we go. So I'm just using Desmos as my calculator. I could also just use a calculator. One way or another, I'll get that it's 1.05. So there's my linear approximation. Now, what is the function really? So that's part C, I believe. So part C is saying compute the magnitude of the error in the estimate. Okay, so if I want to find the error, I'm first going to need to know what the value was. So error is, oh, I better write this down. Error is the difference between the real function value and the estimate that we came up with. I'm actually going to write that down. So different contexts will have you do it different ways. So I'm going to do approximation minus actual. That will be error for us. That's a formula. So different books will have you do actual minus approximation or approximation minus actual. So there might be different reasons for doing them. But basically all that will do, the magnitude of the number will be the same. It's just a question of which way the sign will be. So that's going to be the error in our estimate. Will be the approximation minus the actual. Okay, so if that's the case, then what is it actually? So the actual value, which of course we could find within a certain number of decimal places, is f of 1.1, which is the square root of 1.1, which is, I'm just going to grab Desmos, but again, you could always grab a calculator. I just type SQRT 1.1, and it tells me that it's 1.048808848817. All right, then the error, oh, I don't want to write it like that. I just need to find the difference between the two. So I'm going to take 1.048808884817. I'm going to subtract 1.05, and then I get an error of negative 0.00119. I just did that backwards, didn't I? I said I wanted the approximation minus the actual, and then I just didn't do it. It's because it's arbitrary. It just depends on the book. So some books go one way, some books go another way. So just pay attention when you're doing it and see which way your instructor or the textbook wants you to go. So I'm going to do 1.05, so it's positive 0.00119. See, it didn't change the number, it just changed what the sign was. And I just wrote all that up. So I've got my approximation right here, found with L of x. Well, first of all, I found L of x. Then I found my approximation. Then I found my error. Right? So let me just graph it for you here. So here's 1.5. So 1.1, the actual is right there, which is 1.0488 and some change. Dot, dot, dot. And then the approximation we came up with up above is, oh, I'll do this in blue here. So this answer, oops, I take it back, I'm going green. So this answer right here, the 1.05, is right above it. It's on that line, 1.05, and then there's a little minuscule difference between the two, and that's what we're finding, right? The error right there that we're finding is the difference between these two values, right? It's the vertical distance between the two. So this was the approximation up here, and then this was the actual down here. There's a T in there. Actual. Sorry, my U got lost there. All right, so the vertical distance between the two is what the error is. Now, how would this change if I moved out, if I moved farther away from where my value is? Because keep in mind, everything's built off of 1, right? There's A right there. So I'm building my equation from that as my tangent line from x equals 1. So the farther I get away from 1, the worse my approximation is going to get. You can actually start seeing the gaps over here. Right? So letter D says, you know, how would this error change if we went to 1.2? So error change for the square root of 1.2 question mark. And the answer is that the error would get worse, would get larger, which of course is worse for error. Because the farther we move away from where our equation was based, which was A equals 1. Right, that's where our linear equation came from, the worse the approximation will be. right? The worse this tangent line gets, right? And you can see it over here. The tangent line's not good over here. Right up close to that dot, it's not bad, but the farther we get away from it, the more gap there's going to be. Right? In other words, the tangent line pulls away from the graph, is farther and farther from the graph as we move away from x equals a. Which in our case was 1. But this would always be the case, right? The farther you get away from where you establish your linear approximation, where you establish that tangent line, the farther you get away from where that tangent line is based, the worse this is going to be for you. And I can actually show it to you on the graph. So let me go here. So this particular one, you can see the f of a right there, and then you can see how bad it gets, right? How far away from the line above it would be. I can also show it to you on this other graph here because I have them established. So you can see h is my distance from that point. So everything's built from 1.414. And you can see how far apart the points are now. Look at the y values, 0.488 to 0.405. If I let h get smaller, if I let those points get closer to the basic a equals 1.414, they're closer together. See how close those the green and the black dot are. 0.616 to 0.606, or 6136 to 606. But if I get farther away, those dots get farther apart, and they're no longer anywhere close to each other at 0.32 and 0.21. So the farther you get away from your grounding point, the worse it's going to be, which I believe will actually be the point of the next page. So a couple things. If your graph is concave up, then your graph, your L of x will lie below your graph near A. So if it's concave up, then your graph is going to be low, which means you're going to underestimate, right? If you underestimate, then your error will be negative, right? So let me just assume, for the sake of this argument, assume error is the approximate minus the approximation minus the actual, right? So let's just do that. And if we do that, then our underestimate, right, there's going to be L of x will be here, the real value will be right here. We will underestimate that, which means our error would be negative. Right? Because here's your approximation and here's your actual right there. And then here's the approximate down below. By the same token, if it's concave down, then your approximation's right here. The actual is here. And that means that your error will be, here, let me do it this way. Error will be positive. Right? So, sorry, I'm going to change my color because I used blue for the approximation. So let me just change this. So underestimates, that'll be error negative. Overestimates, that'll be errors positive, right? Because the error is that distance right there. The error is the distance between the approximation and the actual.